Okay, so and for the rest of the lecture, we are going to go over one of the case study work and set, which is adult data set. We are going to work through all these problems. In the meantime, we are going to talk about how to using cross validation to find out the best parameters in the random forest. So this is data. It's called adult data. So this is adult data. It's coming from 1994 census database. So the goal is to determine whether a person can make over 50K a year or not. So I have a bunch of features. We have age, we have work class, we have education, and a bunch of things. And we have a lot of features right here. The target is earning level. I mean, it's a categorical feature, which is 0 and 1, as you can see right here. So it is like less than 50K or like bigger than 50K. And you can see I have all sorts of different features here. In fact, if we and we can read this training data set and a testing data set, right? So this is what we got. In fact, we find out there are 3 different like unique value in target. One is not a number, one is less than and less equal than 50K, one is bigger than 50K. So what we do is we are going to remove those and the target that is not a number, it should be either bigger than 50K or less equal than 50K. So what we do is everything less equal than 50K will be and then the target will be changed to 0. Everything bigger than 50K will be changed to 1. So this is like binary classification problem. So it actually encode like 0 and 1 for the training and the testing here. So this is and every time we do something like that, we will do this kind of an exploratory data analysis. We can do this kind of describe for the training data set, and all of that has like bunch of like categorical data, and some are categorical data, some are like numerical data. I mean, if it's numerical data, it will provide a mean, standard deviation, mean, 25 percentile, 50 percentile, 75 percentile, and the maximum numbers. If it is categorical data set, it will provide a unique like number of unique values, the top values, and the frequent and frequencies. Okay. And since for the categorical data, we don't have those kind of mean and standard deviation. So these will be all like not a number. For the numerical values, all these 3 things, unique, top, and frequencies, they are all being not the numbers as well. Okay, so and we can count and to do the value counter to see how many of that will be 0, how many of that will be 1. You can see this is 24, nearly 25,000 target value to be 0, 7,800 to be 1s right here. So what we can do is we can add first things to create an histogram for all the features. So this is something that you have a look at that. So you can see all these like informations and some like and histogram for each of features. So you have some good idea and what kind of and the distributions you are working with. Some of that and might have some good distributions. For example, the ages, you can see some like distributions and informations. Some of this is just being bar plot. For example, this like work class, they are all and have like 8 different categories. Then that will be just bar plot for this work class and so on. There will be and all sorts of different histogram and bar plot for each features. So what we do is we check this data type and find out that we have integer, we have an object, which is categorical data, and that's what we are getting. So one thing that we see, there's some inconsistency from the training and the testing on the data type. You can see in the training data, we have integer right here. In testing, this age becomes object. And this FMLWGT, it becomes float instead of integer right here. So you see, I mean, that's not really good. So what we do is we need to keep everything consistent. So that means all the age should be integers. Every other, testing data set, which is float, should be changed into integers, such that everything can have the same type. So this is very important to make sure everything has the same type. And also, so we need to make sure our target, they shouldn't be object, they should be simply just an integers. All right, so we pop up our target. So that will be my Y train and Y test. We are going to be using the data train and the Y train as our training data set and build a model based on this training data set. Then we're going to using this testing data set to test as our model evaluation. So the first thing that we do is we can just check the infos to check, and this is a common thing that we should start with. The first thing that we come to our mind, we find out some of the entries as missing values. As you can see right here, for example, work class has 30,000, and however for age is like 32,000. So they are about like 1,800 like missing value for the work class right here. So this is something that we need to be taking care of this. So what we do is we need to treat things separately for the categorical features and the numerical features, because the way that we handle the numerical features and the categorical features will be different. So first thing, we need to check, if the data type is object, that will be categorical features. If the data type is not an object, it will be numerical features. So you can see this is something that come out right here. So what you're going to do is you are going to and to do the two things. First thing is you're going to fill up the missing data with the mode of the categorical column. So basically what you do is you find out the mode for that corresponding columns, then fill up not numbers for those columns. Okay, so this is what you're going to do right here. So this is basically you're going to fill the not numbers with the mode of the columns for the categorical features. And also for the and other things for the training and the testings. Now you see everything is being has no and not a number values. So this is treatment is for the categorials, but if we have missing data for the numerical columns, here we don't have that. But say if we have the missing data for the numerical columns, what you can do is you can use the mean or the medians to replace those missing values, and which is a very frequent use methods right here. Okay, right here we have we have a bunch of categorical data set and categorical features, and what we can do is we can encode those categorical features and work class, educations, like marital status, occupation relations, race, sex, and countries. And what we can do is we can just try to do the dummy codings and for these categorical features. So this can be done using get dummies. So what we do right here is we concatenate those like training with the numerical columns with those and the categorical features after and the dummy encodings. So you do the same thing for the training and the testings. Then after that, we find out previously we only have, I think we only have 14 features. But if we do this kind of and a dummy encoding, so and what is dummy encoding says, if it is, and for example, for this like world class federal government, if it is your world class and for that and specific data entries, if the world class is actually federal government, it will be true. Otherwise, it will be false. So, and each columns, it will only be true or false. And for example, for this world class right here, and for the data entry 2, that means that data entries world class is actually the private, so that will be true. So that's why we changed it, and this like entries will be valued as true. So everything will just be true or false right here. So as a result, after this dummy encodings, we get 105 columns. So you do the same thing for the training and the testings. However, we find out something interesting here. In the training, we have 105 columns, but in the testings, we have 104 columns. So that means we will have one additional more columns in the training data set. So the reason that happens is for some feature values, they only shows up in the training data set, but never shows up in the testing data set, which is and totally possible. And what you can do is you can do the subtraction with the, in terms of the set, you can have a set of the data train of columns, subtract the data test of columns. So as the result, you are getting the actual additional columns, which is the Holland and Netherlands countries. So that means there are some data entries has that kind of feature of the country being the Netherlands, but there's no such kind of data set that actually the countries is being Netherlands. So what we can do is we are going to, and we can add in extra features, which is country, Holland, and Netherlands, to be all zeros on this data testing data set. Once we're adding this columns, both both columns will be identical, then we can move on from it. So you will see we will have 105 columns for the training and 105 columns for the testing. So the first things that we do, and we have to talk about this things already, we're going to train a decision trees with a maximum depth of 3, then evaluate the metric and accuracy metrics on the testing and the data set. Here we just fix our random seeds to be 17. This is just for the reproducibilities, just because we know when we build up decision trees, it actually matters for for like which random seeds that you choose. If you fix your random seed to be 17, that means at every time they were using exact the same seed, and you are getting the same results. So you do the fittings, then you do the predictions, then you're getting the accuracy as being 84.4% of accuracy. Okay, so that doesn't look very good. However, you can do more, trying to do using the 5-fold cross validations to find out the optimal maximum depth, because previously we just choose this maximum depth is being 3. So this is very arbitrary. So what we can choose is we can change this maximum depth from ranging from 2 to the 10. Then you do this cross validations on the grid search for the trees and the tree parameters. for this 5-fold cross validations. Then we train with X train and Y train. As a result, we are find out that the best parameters is 9, and the best score is 85.65, which is, you can see it's almost more than 1% of accuracies for the and for the result. And then so we're getting this and a tree grid. Then we are going to using the same thing and to make predictions for the X index and X test data set. So this is something that you need to keep in mind here, since we already mentioned this X train and X test may not have the same columns, since we are training everything in the features of the X train columns. It's possible that X test has like additional columns that we never actually seen that in the training data set. That's totally possible. So what you can do, just in case, if we have more columns in the testing data set than the training data set, what you can do is you can actually enforce this on using the X train columns as the features. So you can restrict your X test on the features of X trains. So this will be subset of the columns. But in our cases, since like X train and X test has exactly the same columns, so that means this will be just for the X test itself. So then you do and make these predictions, then calculate this accuracy scores. You can see this is 85.8, which is perfectly reflected from this validation data set. And the validation errors from the best scores. So you can see these two are very, very close to each other. So this is really good. But like 85% is not the best. And we can train a random forest instead. So, and we're going to train 100 and the design trees and take these ensembles with the random forest classifiers. So what you can do right here is you fit this an X train and Y trains. However, so this is not the and the scores of that work and output a training data set. And on training data set, you can get training error, but training error doesn't mean much things because it doesn't reflect anything for the generalization error because it can easily get overfit. So what you can do is you can do this cross-validation scores of this random forest for the X train and the Y trains with 3-fold cross-validations. So what I got is basically you do the 3-fold cross-validations on the training data set, and these CV scores, they will give you 3 different validation errors for this 3-fold, and we can take average of this. And after you take average of that, you're getting 85.6% of accuracy, which is very close to the design trees in the task 3 after we pick the best parameters. So you can see right here, and we can also do the same things for the testing data set. You can see we are also getting the 85%, which is quite reasonably good. But I want to remind you, I didn't do any kind of the a parameter search for the random forest. So this is just by default, and all the parameters like by default right here. But you can do all these things. I think that should be 100 trees. But you can also tune in the parameters, which is the maximum depth and also the maximum number of features for each features using this grid search cross validations. So what you can do is you can tune these parameters. You can choose this maximum depth is from 7 to 11, and also you can change this maximum features. And we know the maximum feature that we have is 105, and you can change this maximum features for 5 25, 45, and so on until like 105. So this is basically, and this maximum features that you can choose. And we have a bunch of different and the parameters. In total, we are getting like 25 candidacies for this forest parameter. And we do the grid search cross validations of this random forest classifier. I mean, this is default, but there will be two parameters that we're going to search on the grid search, which is maximum depth and the maximum features here. By using the cross validations is threefold. We do the back and the fit for this, and you can see this actually split and took about 6 minutes. That's a really long time. So because to do this 75 times, and also and each of that will be random forest. We know like random forest will be and slower to train, because for each fit that would be 100 like decision trees that you need to and fit as well. So in total, you're actually fitting 7,500 decision trees. With that, you can find out the best parameter we got is 11 in terms of maximum depth, and then the maximum feature we got is 45. The scores we hear is 86.3. In terms of testing, you are getting 86.4. So these two are very close to each other. So this is even better than and what we got for the random forest. I think that's about 1% more. I mean, in terms of accuracies. So you can see this is how we actually deal with and how to tune the parameters for the random forest, and in particular, and what kind of parameter you can tune for the random forest right here, which is just the maximum depth and the maximum number of features that we can use. Okay. But overall, you have to be careful, because random forest is I mean, if trying to fit one like random forest, I mean, that could be also very expensive, and let alone you want to do this for 75 times, that would take like quite long time. And right here, I think we have I don't remember how. Yeah, we have like 32,000 rows, and you basically spend 6 minutes on this problems, right? So this is quite a bit time to run. All right, so this is a simple case study. I mean, I'm done here, and I think you should be able to do the next homework. I mean, this is very important right here. All right, thank you.